Listen to look into the future. Audio-visual egocentric gaze anticipation. In everyday activities, a person's eye movements and gaze fixations are reflective of their intentions and goals. The ability to forecast where somebody will look next can enhance the emerging capabilities of augmented reality by enabling timely content delivery based on how a person uses their gaze to interact with the world around them. In this work, we address the task of egocentric gaze anticipation, or predicting the future gaze targets of the camera wearer from egocentric video. In this task, the input is a sequence of video frames, and the output is a sequence of gaze target locations for future time steps, which are represented by heat maps. Forecasting the gaze fixations of a camera wearer using only their egocentric view is challenging due to the complexity of egocentric scene content and the dynamic nature of gaze behaviors. However, visual attention is inherently driven both by visually salient objects and audio signals. Audio signals can therefore serve as an important auxiliary cue for egocentric gaze anticipation. We can see an example of this in this video, where the camera wearer's ground truth gaze position is shown with a green dot.
Is it flashing or not?
It's green.
Yours is also green.
In this video, the camera wearer is first looking at an object. The standing person asks a question, and the camera wearer moves their gaze to this person's head. Then, the sitting person on the right answers the question, and the camera wearer shifts their gaze to this person. We can see in this case that the gaze is driven both by visual cues, like the locations of the two people, and audio cues, like the conversational utterances of the people. In this work, we leverage both audio and visual cues for egocentric gaze anticipation. We specifically consider that the correlation of the audio and visual modalities happens in both the spatial and temporal dimensions. Spatially, the visual region that has a stronger correlation with the audio signal is likely to be a future gaze target. For instance, a person's head is likely to be a gaze target when the audio contains a human voice. Temporally, the audio signal may drive the way the camera wearer moves their field of view in response to new sounds. As we saw in this video example, when a person begins speaking, the camera wearer moves their head towards them in response. With these observations as motivation, we propose a new approach for egocentric gaze anticipation that uses a spatial-temporal separable fusion approach for leveraging both the audio and visual modalities. Our work builds upon several prior works on egocentric gaze modeling. Most of these works address the task of egocentric gaze estimation, which takes in a sequence of video frames and predicts the gaze targets for the current frames. However, egocentric gaze anticipation, which differs by predicting gaze targets for future frames, is an understudied problem. This task was first proposed by Zhang et al. In 2017. They addressed this problem by training a GAN to predict future frames and then estimating the gaze for these frames. They improved upon this work in 2019 by adding a separate branch for gaze forecasting. No further works have addressed this problem, and furthermore, no prior works on either gaze anticipation or estimation have used audio signals in addition to the video frames. In our work, we investigate the impact of audio in predicting gaze behavior and build the first audio-visual model for egocentric gaze anticipation. In our method, we first sample video frames and corresponding audio signals. The audio signals are converted to spectrograms using a short-time Fourier transform. Then, we use transformer-based video and audio encoders to obtain embeddings for each modality. The two embeddings are fed into the spatial fusion module. First, all audio tokens at each step are condensed into a single token by a convolutional layer. We then use an in-frame self-attention layer to calculate the correlations between all the visual tokens for each frame and the single audio token at the corresponding time step. The connections across different frames are ignored. In this way, the model captures the correlation between the audio signal and its corresponding visual features in space. We also propose a temporal fusion module that works in parallel to the spatial fusion module. The video and audio embeddings are first condensed into a single audio token and a single visual token at each time step. They are then input into a cross-frame self-attention layer to learn the relationships between the two modalities across time. The outputs from the two fusion modules are merged by reweighting to get the final visual representation, which has been refined by spatial and temporal correlations with the audio signal. Finally, we use a decoder to upsample the visual representation to a higher resolution, producing the predicted gaze heat maps. In addition to supervising the heat maps, we use contrastive learning to learn a more robust audio-visual representation. Like we did for the visual modality, we also reweight the audio embedding using the audio outputs from the two fusion modules to obtain an audio feature that has been refined through correlations with the visual modality. The reweighted audio and visual embeddings are mapped to a common space, and a contrastive loss is applied to leverage the intrinsic alignment of the two modalities. We conduct our experiments on two egocentric video datasets, Ego4D and ARIA. Both of these datasets contain audio streams and eye tracking data, which provides the ground truth gaze targets. These datasets capture social scenes and daily activities in home settings. We trim the long videos into 5-second video clips and use the first 3 seconds as the observed video segment, which is input to our model, and the following 2 seconds as the anticipation segment, which are the time steps for which our model predicts future gaze heat maps. The video encoder is the multi-scale vision transformer model initialized with weights from Kinetics 400 pre-training, and the audio encoder is a lighter weight multi-scale vision transformer with Xavier initialization. We use KL divergence loss for supervising the gaze heat maps and multimodal NCE loss for contrastive learning. Our evaluation metrics are F1, recall, and precision. We first evaluate the contribution of each component in our proposed model. We consider a vision-only version of our model with only the spatial fusion module, our model with only the temporal fusion module, our model with both fusion modules but no contrastive loss, and finally our full model with contrastive loss. We see that using the audio modality is indeed useful for this task, and using both the spatial and temporal fusion modules along with contrastive loss learns the most effective audiovisual representation for this task. We compare our approach with state-of-the-art methods for egocentric gaze modeling. We observe that our model outperforms the best gaze anticipation models, DFG and DFG+, by more than 2% in F1 on both datasets. We also adapt models designed for egocentric gaze estimation to the anticipation task. The results show that these models also serve as strong baselines for anticipation, but our proposed model still surpasses these approaches on both datasets, achieving state-of-the-art performance. We also break down the overall anticipation performance into performance at different future time steps. Unsurprisingly, forecasting gaze is more challenging as the time step increases because of the increasingly distant relationship with the observed video segment. Our method consistently outperforms all baselines at all future time steps. To evaluate the generalization capability of our approach, we also adapt our model to the egocentric gaze estimation task by replacing the labels of future gaze targets with gaze targets on the current frames. Our approach exceeds the prior state-of-the-art approach by 0.6% on Ego4D and 1.3% on ARIA in F1. This suggests our model can generalize well to other egocentric gaze problems beyond gaze anticipation. We further study what our model learns by visualizing the correlation weights between the audio token and visual tokens in the spatial fusion module. The highlighted areas suggest stronger correlation with the audio stream. We find that our model captures speakers when they are talking and stops focusing on them when they stop speaking. These examples provide further evidence that our model has the capability to capture the audio-visual correlations in space to learn a robust audio-visual representation. Finally, we show some video examples with forecasting results from our model.
Is it flashing or not?
It's green.
Yours is also green.
As we see in this first example, in the observation segment, the standing person asks a question and the camera wearer moves their head towards them. The sitting person answers the question. In the anticipation segment, our model successfully predicts that the wearer attends first to the location of the standing speaker and then shifts their attention towards the sitting speaker.
Oh, oops.
Oh, jeez.
Shoot, sorry.
Yeah. Oh, sorry.
Oh.
In the second example, the camera wearer spills a drink on the table and looks at the table. The other person begins speaking, and the camera wearer shifts their attention to this person, which our model successfully predicts. To conclude, in this work, we build the first computational model that uses both visual and audio signals for modeling egocentric gaze behaviors. We propose a novel fusion approach to capture the audio-visual correlations into spatial and temporal dimensions separately, achieving state-of-the-art results on 2 datasets. We provide insight into our approach through detailed ablation studies and visualizing the audio-visual correlation weights learned by our model to show interpretability.